and then I'll post a VOD later. Okay, so welcome to chapter 2. So hopefully everyone was good with the last sessions stuff. If you want, we can take a few minutes to get help with the problems. If not, can launch right into the stuff. So nobody wants does anyone have any questions for the last one? Yeah, so if you have any questions, just please let me know which ones you have. Cool? If not, we're going to start straight into chapter 2. Okay, so in this chapter, we're mostly going to be going through three concepts. Basically, the idea of constructing a vector space from a set of basis vectors, right? So this is actually a very important concept in mathematics all around, where you would have maybe you have like a topological space from basis, or maybe like a ring, or basically you have smaller things and you want to use those smaller things to build a bigger thing. So in the sense that like you can study the smaller space and then you get more information about a bigger space. So one way we can do that is by dealing with basis. So what we're gonna do is to introduce the notion of a basis. We probably need to introduce the notion of linear independence. So if you recall from maybe I don't know, like high school, what you have vectors which that are perpendicular to each other, right? So consider, say, the three-dimensional space, right? Intuitively, there are three vectors which are all perpendicular to each other, right? And if you're like 4 dimensions or like 5 dimensions or whatever, there are also like 4 or 5 vectors which are perpendicular to each other. Although we can't visualize this in 3D, obviously. And that's what linear independence is trying to capture, right? We are trying to basically encode the notion of vectors being perpendicular to each other in an arbitrary number of dimensions, right? So first, we need to discuss the idea of a linear combination, right? So you might have seen this before. If you look at like integers, right, you have the as plus bt thing. Well, this is basically that idea actually came from vectors, where we define a vector being made up as a linear combination, which basically says, let's say we have a bunch of vectors, and then we just scale each vector and we add them all together, right? And this is like the most crucial notion that brings us to span. Right. So for example, with 17 negative 4 2, so this is this is one linear combination the book gives, which is non-trivial. I'll give you the trivial one, which is basically, let's say you have the vectors 1 0 0, 0 1 0, and 0 0 1, which are, you can think of it as ijk or something. I don't know if you're used to that. And that'll be basically like 17 times the first vector, which is 1 0 0, plus negative 4 times the second vector, which is 0 1 0, and 2 times the last vector, which is 0 0 1. And so that this vector here, any vector here, is being expressed as a linear combination of some vectors in R3. And you notice that the combination I gave you just now, like the 0 1 0, there's 3 of them, right? Which is, it's not a coincidence that we required 3 of them. So from that we can give the definition of a span, which is basically saying that the span basically says, okay, if we have a list of vectors v1 through vm, right, we take the set of all possible linear combinations of these guys, right? So imagine like enumerating, in a sense, through every field element and just scaling each v1, so from like 0 to whatever, and then just add them up all together. So it's basically, but you don't think of we don't like to think of span as the as individual vectors, but rather as the whole space of possible vectors in there, right? So if you say I pull a vector from the span, then I know exactly it's going to be a linear combination of the vectors I gave to the span, right? So for example, if w is some vector in the span, then I know it's certainly a linear combination of these guys. Note that some of the coefficients might be 0. That's totally fine. Yeah. So and then now we move on to the idea of why it's small. So the span is the smallest containing subspace. What does that mean? It means that if you have any subspace that contains all of these vectors, right, say v1 through vm, then it must also contain the span. So I think we believe we went into this the last session, a similar idea of being like the smallest and the smallest subspace. And this is also the same idea And in fact, there is a connection between the direct sum, I think it's the sum and the span, which we'll leave for the reader to figure out on their own. And so if we take so as you can see here, the proof, it's pretty trivial, so we're just not going to go through it too much. And then we can also say that a list of vectors spans a space, right? So if you take a list of vectors and you construct a span, right, that's a vector space. But conversely, if you have a vector space and you have a list of vectors that such that the span is equal, then those lists of vectors actually spans the whole space. And notice that these guys here, which is a pretty these guys here would if you take the span of them, it actually makes up the whole space of f of n. So for example, if you have r of n, right, then again 1 in each slot and 0 everywhere else for each the ith term for each of that guys, that basically makes up the whole of Rn. And now we can finally give the idea of a finite dimensional vector space, right? So if we have a finite dimensional vector space, right, we need a list of vectors that spans the space. So it's quite important to realize that lists here are actually finite dimensional, right? So it's finite length. Lists have to be finite length. So if you don't have, so it is true that you do have infinite dimensional vector spaces, and you would have an infinitely long list of vectors that spans the space, but this thing is not really a list anymore. It's more of a sequence. Although you could think of every list as a sequence where all but finitely many terms would be 0. Yeah, so as you can see, by definition, every list is finite length. And then of course we have, and of course we can talk about the space of polynomials over a field, which is also another very important thing. So this really goes to show you the power of the idea of a linear algebra, where we are now taking polynomials and even functions, and we're working with them we're treating them as vectors, and we're doing linear algebra in them. And as you can see, if you think of a polynomial, right, as basically just the coefficients, right, and these guys, so the one is a vector, z is a vector, z squared is a vector, and so on, so on, so on, right? So if those guys are vectors, right, then the coefficients, these are the scalars. And in fact, that means that the polynomials are just linear combinations of 1, x squared, and so on, so on, so on. Now, I assume everyone knows what a degree is. So at this point, does anyone have any questions, or are we all good?
I have a quick
Yes.
question about polynomials. So we're talking about polynomials in the context of vectors and dots.
Yeah.
In the context of functions and okay.
Yeah. We're just thinking of themselves. Yeah. So they're just functions, right? So the set of like polynomials treated as a vector space would be in fact a subspace of your space of all real value functions, which we discussed in the previous session. And more notation, blah blah blah. Yeah. So an good example of an infinite dimensional vector space is, of course, the set of all polynomials over some field. So for example, the set of all polynomials with real coefficients would be a infinite dimensional space, and also the set of all, of course, all sequences, right? Obviously, that's infinite dimensional. So this is pretty clear, and we now want to talk about linear independence, right? So linear independence, basically, so this book gives the idea of linear independence, right, of vectors v1 through vm, saying that there is only one unique way to get the 0 vector from these linearly independent vectors, which is by setting all the coefficients to 0. There is a very similar definition for linearly independent, which would basically give you the idea that which would basically say that no vector in the list is a scalar multiple of some of a linear combination of other vectors, and these are in fact equivalent definitions, which you will prove in the exercises, of course. So we go to some examples of linearly independent lists, and you notice just now that I gave the list of 1, 0, 0, 0, 1, 0, and 0, 0, 1 for the case of 3 dimensions. And turns out that these guys are in fact linearly independent, where you can kind of visualize them as the unit vectors, starting from the origin, as the unit vectors in R3. And you can kind of tell that these guys are linearly independent, right? Because there's no real way to like get to the other one by scaling it. So that's the intuitive idea of linear independence. And now we can now give the definition of linear dependence, which is simply just a negation of linear independence. So a list of vectors would be linearly dependent if it is not linearly independent, right? Because these guys are just the negation of each other, right? So it's quite easy to find two vectors that are linearly dependent. For example, say we have R2, right? If we take 1, 0 and 2, 0, right? 2, 0 is certainly, like, these guys are certainly linearly dependent. Intuitively, I believe there's actually a good video on YouTube made by 3 Blue 1 Brown, where he basically like shows that like one of them will be scaled onto the other. You know, it's a pretty intuitive notion of that idea. And in the definition of this book, you notice that there's actually a way to make 0 with 1, 0 and 2, 0 just by taking 1 times 2, 0 plus -2 times 1, 0, which will make 0. And those coefficients aren't 0, which means that that doesn't work. So it would not be linearly dependent anymore. So we now go on to a very important lemma. And this is arguably the most important lemma of this section, right? Because it gives you a lot of tools, and this is a very important thing that you use often in linear algebra. So we'll actually be going through the proof and to show you some applications of this lemma. So first, it's called the linear dependence lemma. So it's saying that if we have a linearly dependent list, we can there will be a vector vk in this list here, such that it is a span of all the other vectors. So basically, all the other vectors removed. And what this means is that if the kth term is removed from this list, the span of the remaining list does not change, right? So basically, this is telling us if we have a linearly dependent list, right, we can kick out a linearly dependent vector, and then we still have the same space if we span it. So the proof is quite simple. The entire notion, right? So basically, the idea is that since this list is linearly dependent, we apply the definition and conclude that we have coefficients that aren't all 0, such that they sum up to 0, right? So it is possible that so basically we want to take the largest k, right? So basically the last k in the list, right, such that the coefficient isn't 0. And then what we basically do here is we divide everything in the list by a k, and we subtract. So by dividing everything by ak, right, intuitively what is happening here is that all the scalars, all the coefficients get scaled down by ak, except at the term at akvk. What happens is that akvk divided by ak is vk. So we just move that over to the right side of the equation, or in this case it's the left side, and on the right side we have a equation for vk. And this is why we required it to not be 0, because what's happening here is that since we divided everything, we can't divide by 0, of course. And so this shows us that vk is in fact a linear combination of v1 through vk minus 1. And because it's a linear combination, that means it's in the span. And what you could actually do now is that, and now we can basically say, to the next part of this proof. So this is shown this guy here, right? So this next part of the proof is basically showing that we can just throw it out of the span. But like that's quite intuitive at this point, because so the whole idea here is that since vk is in a span, right? If you have any a1 through v1 plus like any sort of linear combination of the original list v1 through vm, right? What's happening is that if you replace vk with this expression here, right? And then you shift some coefficients around, and vk basically disappears from the entire thing itself, which means that vk have been thrown out of the span. And this is basically the whole idea of the proof that's going on here. And so what happens now is that vk has been kicked out of span, and thus the span still stays the same. And so that basically is the whole idea of the proof. You can kind of go through yeah?
I got a quick question.
Yeah.
So in the first part of the proof, to show that vk is in the span, right?
Yes.
When you divide ak over, when you divide all the other coefficients over ak, that only works if the quotient of them is also in the field.
Well,
correct?
Luckily, this is the nice part about fields, right? Recall that with the field, every element can be quotiented, right? Inverted, which is why we want to do it with fields.
Yeah,
right?
When we define the field, yes.
Exactly. So this is why we like fields so much, right? So
okay.
Yeah.
Proof holds because A1
over AK is in the field, right? So the author doesn't explicitly call attention to that, but that's a very good point you brought up, right? Because it turns out there are like extensions and theories of linear algebra that don't require fields, and in fact, your complaint is quite valid for those cases, those special cases. Yeah, but in this case, since we're working with fields, these quotients are all defined, right? Because they're all inverses, and therefore it's completely fine. Does that make sense?
It's perfect. Thank you.
Thank you. All right, fantastic. Okay, so we're just gonna look at an application of this lemma here, the linear dependence lemma. So we're gonna look at this list here, right? And
Albert?
Yes.
Yes. Can I quickly just clarify? What does the sum of vectors? So you said A times V1 times V2 times V3. If you like scroll up the previous page, what does that have to do with linear dependence exactly? Because
which one here?
Vectors were, yeah. Because I thought they were linearly dependent.
Linearly dependent. This is the definition.
Yeah, but why do we sum them?
Because it's the definition, right? We are applying the definition of the list being linearly dependent, right? So recall that linear independence means that there's only one way to make this, right? So the negation of linearly independent means that basically since all of these are 0, so the negation of linear independence means there exists one, there isn't 0. Make sense? There exists a scalar that isn't 0 such that the sum here is 0. Yeah?
I see. Kind of. That's still is a bit confusing. I just thought that linearly independent vectors couldn't be expressed as scalar multiples of each other. Isn't that
correct? So, because the thing is that this list is linearly dependent. Linear independence means that the vectors in the list cannot be expressed as scalar multiples of the other vectors, right? So for example, let's easy example. Let's say we take the unit vectors in 2 dimensions, right? So you notice that if you pick one of the unit vectors, right, there's no way to express it as the other unit vector, right? In terms of a scalar multiple, right? You might get this.
Would be like independence.
Yes, so 1, 0 and 0, 1 are linearly independent.
Okay.
Yeah. Does make sense?
Yes, that does.
Cool. All right. Yep, good. Very good question. Thank you very much. Okay, so we're going to move on to the example of applying the linear dependence lemma. All right, so we take this list, right, in R3. So we have a list of length 4. The fact that it's 4 is probably already suspicious, right? Like, it probably already calls to you that it's going to be linearly dependent because R3 seems to have dimension 3, right? And so we apply the linear dependence lemma to find out which one of these vectors in the list would be actually dependent on the other ones, right? It turns out that it's not going to be this vector or the second vector, right? So it basically goes through it with you, right? So this is useful if you want explicitly to find what vector it is. You kind of just iterate through it. And it turns out that the third one is apparently a linear combination of the first 2, right? So it turns out that we can just throw out the third vector and the rest have the same span. And so we now come to an important notion, which is the idea that a length of a linearly independent list must be less than or equals to the length of a spanning list, right? So what does this mean? So if you look at this list here, right? This is 4. This is length 4, and this is R3 can be spanned by 3 vectors, right? The 3 unit vectors, the 3 unit vectors at each of the dimensions, right? So since this list of length, this is length 4, right? And this is length 3, right? If this list was in fact linearly independent, then 4 is less than or equals to 3, which is untrue. So therefore it must be linearly dependent. And so, so this proof, it's it's quite routine. I think we're just gonna give we'll just kind of give the overview of what's going on here, and we'll motivate this idea, right? So what we're basically taking is we take a linearly independent list here, and then we take a spanning list, right? And what we can do is if we take a list that spans it, right, we can basically stick all the linearly independent vectors on top of this list, right? And then we and we use this lemma here to like basically kick out the linearly dependent vectors, right? Which none of these UIs would get kicked out, because each of the UIs is linearly independent and they cannot get kicked out, right? Because those guys would need to have 0 coefficients. And you basically repeat this process here until you kick out all of the linearly dependent vectors. And then there's the remaining vectors, right? The remaining vectors here would be of length less than or equals to your spanning list, because your spanning list is of length n, and your linearly independent list is of length m. Right? Of course, it is possible you've kicked out all of your elements in your spanning list, right? And yeah, so basically that's the whole proof here. Is everyone still following along now? Did I go too fast? Everyone's still good? Cool. Okay, so by the way, if there's any noise, I do apologize for it. Yeah, so we're going to move on to the examples here. So it turns out that what I was pointing out just now about the length of list of length 4 is actually coming to question here for this example here. So what's happening is that since we have a list of length 3, right? It spans R3, right? You can't have any list that would be linearly independent in R3 would have to have at most length 3, right? So obviously this is length 4, so it cannot possibly be linearly independent. And this is also another idea. So no list of length 3 spans R4. Right. Yeah, so what's going on here is that basically it's saying that if you have a list that's shorter than 4, right? If it's not exactly 4, it's not going to span R4 because one of these guys won't be hit, right?
Robert?
Yeah?
Lists, they're ordered. We can't change elements in them, right?
Yes, the order of a list does matter. But you'll soon see, and actually one of the problem sets, right, where I basically said that I basically asked for you to show that if we replace list with set, it basically still stays the same. Yeah.
Oh, but set.
Yeah, sets are unordered, but it turns out that the theory of linear algebra basically doesn't change much at all if you replace list with set.
And then that means. Oh, okay.
Yeah, it's just a problem for you to think a little bit about. But basically the idea here is that the book uses a list, so we're gonna go with the book. But it is interesting to note, and it's actually quite important, that linear algebra really doesn't care whether you're taking lists or sets, right? Because most of the time we're using linearly independent lists, and of course, if your list is going to be linearly independent, then you gotta be using sets would work just as well. Yeah, and another reason why we can use sets is because the vectors, you can commute the vectors, right? Like v1 plus v2 is the same as v2 plus v1, right? So in the sense that linear combination with the list, it doesn't matter if you just swap everything around. Does that make sense?
Kind of, yes, but what doesn't is that if we turn every list into a set...
You can't turn every list into a set. Because I think what you are concerned about is that maybe you have a list with duplicates in there, right? And then if you turn it into a set, that will basically delete the duplicates.
Yeah.
Yeah. So it turns out that some of these proofs will require a small modification to them, but the theory that all the ideas here behind it doesn't change at all, right?
Okay.
Yeah.
Yeah. Thank you.
So that is the first problem, I believe. Yep. Anyway, so now intuitively what we can now move on to the idea is that if we have a subspace, right, of a finite dimensional vector space, let's say U is a subspace of V, then U should also be finite dimensional, right? And yeah, I mean, intuitively that makes sense, and of course it should make sense, right? And this is basically the proof for it. So if it's trivial, we just ignore it. So what we do is we take a vector. So this is actually kind of nice, because it also sometimes lets you choose a basis for a infinite dimensional vector space. Sometimes. It doesn't always work, right? So what's happening is basically we pick a non-zero vector in U and span it you keep spanning it, right? So you keep adding things until you get to the span of U, right? And basically, since what we're doing here is, let's say we pick, first one is we pick U1 that's in U, right? And then we basically choose another U2 such that U2 is not in the span of U1, right? Since U2 is not in the span of U1, that means U2 and U1 is linearly independent, right? Now pick a U3 such that it's not in the span of U1 and U2. Since U3 is not in the span of U1 and U2, it's U1, U2, U3 is linearly independent. And then you repeat this process until you make a U, which is spanned by linearly independent lists. Linearly independent, which is spanned by some vectors, which form a linearly independent list. Sorry, just quick digression. Sometimes I say vectors are linearly independent, and sometimes I say that a list is linearly independent. These kind of mean the same thing, right? So what it means is that basically, like I said, if some vectors are linearly independent, then the only choice that makes the linear combination of 0 is 0 for each of those vectors, right? So if there's any concern about that, right, then that should hopefully clear it up, right? So if U is so what we're doing here is that since we have taken a span, right, and U is spanned by linearly independent vectors, right, we now return back to our lemma, which says that if we have a linearly independent list, then it must be less than or equals to the length of the spanning list of the space, right? So say the list length of the spanning list of V is length n, right? Then since U is spanned by linearly independent vectors, the length of the list of U of a list that spanned U must be less than or equals to n, which shows that U is finite dimensional. Does it make sense? Hopefully that all made sense. If I'm going too fast, please let me know. All right. If
the proof, excuse me.
Sorry.
Just a quick question. So the proof for the 2.25
yes,
is just a repeating step. It's like a recursion until we find a UK.
Exactly. Yes.
Okay.
You can even try to. This proof can be kind of rewritten with induction. If you want, it's a fun exercise to try to rewrite it induction. If you don't want to do it, that's fine. Everyone's sick of discrete. I get that, right? But yeah, we're implicitly using induction when we write this proof. Does it make sense?
Got you.
Yeah.
Yeah. Thank you.
All right. So if the first part did take a bit longer, so we're half an hour in. So if anyone wants to if you want, we can either so there's two options here. One, we can take 10 minutes to work on the problems, and the other option is we don't do the problems and we just move on to 2B. So anyone wants to do problems, I'm gonna start a poll in the general channel. React with 1 and move on 2. So react with 1 if you still want the problems, and react with 2 if you want to move on to just doing shit. Okay, so if you want to take 10 minutes to do problems, we got that. Okay, so it looks like majority of people want a 10-minute break to do problems. So let's take a 10-minute break to do problems, and I'll see everyone back at 3:43. Well, I mean, I'm not going to be leaving. I'm going to stay here and answer your questions. So feel free, if you have a question, please feel free to unmute, right? And again, please let me know if you have any questions. I'll be here for the next 10 minutes to help you with problems. Cool?
I have a quick question.
Yes, of course.
Yes, could you please explain linear or finite dimensional and
yes, of course. Finite dimensional. So you forgot finite dimensions, right? So if we bring ourselves to if we bring ourselves to definition 2.9, right? A vector space is finite dimensional if you can find a list of vectors, right? Such that the span of the list is a space, right? So, for example, let's say we take R5, right? So I can easily give you a list of that spans it. So for example, 1 0 0 0 0 and basically like 0 1 0 0 0, so on, so on, so on, right? So there's 5 of these guys, the unit vectors in each of the dimensions, right? And that is a list that spans R5. So R5 would have to be finite dimensional. Does that make sense?
Yes. And what is an example of an infinite dimensional?
What is an example of infinite dimensional vector space? The set of all polynomials over the real numbers.
That doesn't really make sense.
Okay.
Could you elaborate on that,
Sure.
please?
So if we have the set of all polynomial functions over the real numbers, right? Let's say let's try to prove this by contradiction, right? So suppose somehow it was finite dimensional, right? Say we had the list of polynomials that basically the span of these guys would be the whole space, correct?
Wait a second. I think I might have gotten lost.
Mm-hmm. Okay, no worries.
Why would we have a list of polynomials over our all real numbers to begin with? Like, why would that be useful? Why are we?
Sorry, could you repeat the question?
How is that possible? How can we have a list of all possible polynomial functions for a set of real numbers? How is that? What does that give us?
Yes. So you basically you just realized you finished the proof yourself, right? You just basically showed that that's impossible because that's a contradiction, right? How the hell could you have a list of how the hell could you have a list of polynomials that basically that the span is all of the polynomials, right? You just proved it yourself. Yeah.
Okay.
Cool.
Then that's
smart.
Yeah. I see.
Yeah. Well,
Okay.
good job. This is why you ask questions, because you figure out how to solve it yourself.
I see.
Okay.
And
So
again, for polynomials.
Yep.
Yeah, unless anybody else has a question.
if
Okay.
anyone at all has a
For
question,
polynomials-
please ask. All right. You what?
Okay.
All right. Hello. Okay. Albert. Hello, Albert. Please ask a question. I'm sure you have many questions. Would you like to ask a question?
Oh.
No. No. I'm Albert. Do you have any questions? Okay. How many of you are so lost you can't formulate questions, right? If you are so lost that you cannot formulate questions, react with 3 to my previous message. I won't judge. If you're so lost you can't formulate any questions, please react with 3. Okay? Okay, let's see. Okay, so all right. Where did I lose you guys? Okay, that's quite a lot. Where did I lose you guys? Okay.
I think I'm gonna be real. I don't really understand the span stuff.
You don't understand the span stuff? Okay. What don't you understand about the span stuff?
I see the definitions, but it's just not intuitive.
Right. The definition doesn't intuitively make sense, right?
Yeah.
Okay. So I'm gonna try to give you intuition right now, but the most important thing, that's gonna have to happen, is that you're gonna have to do a bunch of practices to get used to span, right? So basically, imagine. Okay, so close your eyes and imagine a 3-dimensional space, right? Imagining 3D grid or something, right? So can you see how if you take unit vectors, right? Just now erase the rest of the grid and just take the 3 unit vectors, okay? Okay, now what you want to do is imagine all the possible, let's say we take one vector, right? Let's say we take the unit vector let's take the z-axis, right? If we take the unit vector, right, we first consider the set of all possible, scalars of the z-axis, right? if you take the unit vector, imagine the space of all the possible scalar multiples of this vector, right? That will make the whole z-axis. Yes? So, does it make sense?
Wait. What about like if it doesn't?
It will, because okay. So let me. Okay, do you want me to write down the definition? I can give you. Okay, so let me say. Okay, I'll show you an example. So if we write, say, span of the list 1.
Not streaming.
Okay, so no, I'm typing it up right now. I'm not streaming it right now. I've sent it in the general channel. So, text it is just downloading this image. Yeah. So, does this make a bit more sense? So now I'll give you a bit of a less trivial example. Okay, so I'll give you the span of 3-dimensional space. Okay, so if we write these guys here, sorry, this will take a bit of time to type. Okay, so that last set here, right? This is nothing. This set here. So if, sorry for the bad typesetting. This set here is actually just equals to Does this make a bit more sense?
Yeah, I'm talking about like the ones that don't look like that.
What do you mean the ones that don't look like that?
Like, what if they're not 1 0 1 0?
That's fine. It doesn't. So the idea is that it doesn't really matter what you put there, right? Let's say I put something like okay. Let's say we take the span of 5 2, and pi and e or something. Let's say we take the span of this list, right? That would just mean we have x 5 2 plus y pi e. X, Y, in. Right, if we take the span of that guy there, that will be this, correct? Do you agree?
Yeah.
Okay, that basically just means, and then recall how you just add up them coordinate-wise, right? So it's just 5x plus pi, y pi. Yes, that screenshot is pretty good. And then 2x plus ye. Does this make sense? Yeah, the picture is good. Thank you very much, Catherine. Well, okay. The last message, any two vectors that are on the same line that will form a span at R2. So not quite. You can span, as in you can just take one vector and span it. It will form a line, right? But it won't span all of R2, right? You can span anything, right? You can span a bunch of vectors, but like it might not be interesting, right? Like I could span a list of all just 0 vectors, but it would just be 0.
Mm-hmm.
Yeah.
I see, okay.
Yeah, but the picture is nice. Yeah. So basically the span is basically the set of all possible linear combinations, right? So again, how do we think of this? We think of this more as like if I take a vector from this set, right? I know that it must be a linear combination of the span. Oh, sorry. It must be a linear combination of the list of vectors. Right?
If we take a what?
If I take a vector from the span, right? If I take a vector from the span, then I know it must be a linear combination of the vectors in the list, right? So let's say I take the span of this list, right? Then like say I take the span of the list 5, 2 and pi, e. Right? So if I take a vector from this list, I know that it must be some linear combination of 5, 2 and pi, e. if I take a vector from the span, it must be a linear combination of these two. Does that make sense?
Yeah.
Okay,
So-
cool. Yeah.
Yeah.
Yes.
Okay. Thank you.
Do you have a question? I thought you were gonna ask something. You wanna ask something?
Me?
Yeah, because you had a so or
I
something.
think I'm good. I think I'm good.
Okay, we're good. Length of linearly independent list less than or equals to length of spanning list. Can you explain this part? Okay, looks like Kian has got whoever. So we're going. So now it's 3:44. So I hope you have a good break. You may have worked some problems or you went to eat some food or whatever. All right. So let's move on now to the idea of basis, right? So since we now have the tools, we actually now have the tools to talk about basis for a vector space, right? So a basis is nothing but just a list of vectors in a vector space that is linearly independent, right? And the span of this list is the whole space, right? And you might notice just now that I gave you for R2, which is like two-dimensional space, it's 1, 0, and 0, 1. And it turns out that not only these are two vectors that are linearly independent, and in fact they span R2. So that would form a basis of R2, right? And what about so if we take this B here, right? So for example, for example B. So suppose F the field is R, right? So 1, 2, and 3, 5. These are linearly independent in R2, and the span is R2, which it's not too hard to see. And so why is the span R2? Exercise for the reader. Well, in the sense that I'll just give a small hint of the exercise, right? So the idea here is that if you take any number in R2, right, any vector x, y in R2, right, you should be able to find coefficients for coefficients a, b, such that a times 1 plus 1, 2 plus b times 3, 5, that will make up any x, y. And how do you do this? You actually do this by your standard systems of linear equations, which you probably learned in high school. And so, yeah, there is a deep connection between systems of linear equations and linear algebra. There's no coincidence. We will go into that. But basically, that's how you would show that, anything can be reached by that. Yeah. And, well, these are pretty easy, right? So now we move on to how can we check that something's a basis, right? So, yeah?
Question about the basis, yes.
Mm-hmm.
So, relating to what you said earlier, if two basis vectors, for instance, span space, or no, well, yeah, I think you understand what I'm saying. Can we take any number of vectors from the span and then get those two basis vectors we originally had?
So, okay, so you're saying that if I have a list of vectors that span a space, right?
Yeah.
Then you're telling me that we can always find, so if you're saying that we can extract the basis from a span. Is that correct?
Yes, can we do
Yes, you can. We will prove this later.
Okay.
Yes, but yes, thank you. That was a very, very, very good question, right? Thank you very much. Yes, we can do that. And we will, in fact, prove this theorem in a bit later, right? So first we move on to how do we check something's a basis, right? So we say that a list V1 through Vn is a basis if and only if, right, for every vector V in the V, right, there is a unique way such that V is a linear combination of V1 through Vn, right? So what does it mean unique? It means that each of these coefficients, right, A1 through An, if you got V, right, there's only one possible choice of coefficients that forms V, right? You can't have two different choices, right? And why is this true? So if we look at linearly dependent lists later, right, you notice that there are some vectors which you can form by choosing two distinct choices for coefficients of the vectors, right? But they form the same vector, right? And this is why that's an if and only if, right? The proof is again not too hard, right? So what is this? So what is this proof doing, right? So we are only looking to show that something is unique, right? So suppose we have two pairs of coefficients, right? A1 through An and C1 through Cn, such that V is also equals to these guys, right? Note that here we don't need a proof by contradiction. So what it's doing here, right? Since v is equals to a1 plus dot 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 plus an, right? And it's also equals to the linear combination of v1s through vn made by c1s through cn, right? What we can do is just subtract, because these are both the same v, right? So if we subtract c1 v1 plus dot 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 plus cn vn from a1 v1 plus dot 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 plus an vn, right? You get this, right? And so let's actually have a look at what 2.29 is, right? So if you have this, right, and we subtract this on the across, right, the left side is 0, right? And so the right side, so this is also 0, right? And since v1 through vn are linearly independent, right, all of these must be 0 as per the definition, right? So since each of this is 0, you just add across it, right? So that means a1 equals to c1, b1 equals to a2 goes to c2, and so on, so on, so on, right? So since these two are equal, they're unique, right? And for the other direction, we're not going to bother proving it. It's quite trivial, right? You can look at it at your own time. So so it's important to note that a spanning list may not be a basis, right? As Catherine pointed out just now, which is very good thing to observe, right? You can always extract a basis from a spanning list, but a spanning list may not always be a basis, right? For example, you can span R3 with like I don't know 100 vectors, right? But that's not a basis for R3, right? So if so here's the thing we're gonna prove, right? Every spanning list contains a basis, right? So we're gonna prove right now that we can always extract a basis out of a spanning list, right? So we're gonna go through the proof because I think this is also kind of important, right? So say we had v1 through vn that spans in fact v, right? We just need to kick out some of these vectors from here, right? The ones that we're actually gonna kick out is, of course, the linearly dependent vectors, right? So we just apply the linear dependence lemma, right, which we proved like sometime above there, right? So 2.19, and what we're doing is we take this list, right, and we kick out. We keep kicking. First, we kick out all the zeros at the start, right? So why is this? So why do we kick out all the zeros at the start? Because if we don't kick out the zeros at the start, this will end up deleting everything. So first of all, we kick out zeros. This is just a small technical adjustment. Then next of all, what we do is we go through the list, right? If basically we just check, okay, if the second, so say if v2 is in the span of everything else, right? We delete it from there because it's linearly dependent, right? And then we keep repeating this, right? Imagine an iterative process, right? Like a computer, right? You iterate through your list, right? You pick out the vectors that are linearly dependent and you kick them out. Right? After you kick out all of these guys, right, you have gotten a list that is linearly independent, and the span is still going to be V, right, which shows that this linearly independent list is now a basis. So, and that is basically the whole proof of that, right? And now we come to basically a very important theorem, which says that if you have a finite dimensional vector space, it must have a basis. So it's also interesting to note that this is true for infinite dimensional vector spaces, but your basis wouldn't be a list anymore, it'll be a set. So, of course, by definition, a finite dimensional vector space is a spanning list, and then that's quite easy, right? And so now we ask a kind of an inverse question, right? So if we have a spanning list, right, we can extract a basis from it, right? If we have a linearly independent list, can we get a basis out of it? And it turns out the answer is yes. And this is also, again, a very important tool, which we will apply very often in chapter 3. So the theorem statement says that if we have a linearly independent list of vectors in a finite dimensional vector space, right, we can add vectors to it such that it is a basis, right? Such that after you add all these vectors, it will become a basis of the vector space. The proof is not too hard. So again, what we do here is we take our linearly independent list, right? We take a list of vectors that spans it, and then we just put them together to make a new list, right? Just basically adjoin